Thanks very much. It's great to be here in Toronto, and in fact, Montreal. Toronto was every year I came to Toronto to interview undergraduates from Canada to Cambridge. And it's just the pandemic stopped it. So Canada for me is coming to Toronto to interview. But last time I've been to Montreal was 25 years ago when I was a student coming up from MIT to see Quebec. So it's great to be back. And I'm here to tell you about learning quantum mechanics using embedding, polynomials, and composition. So first, let me introduce the range of materials modeling methods that have evolved over the last 50 years. They span a huge range of length and time scales. So over here on the left, we have quantum chemistry. Essentially, we know how the world works. We know the equations of matter. We know if you place a couple of atoms somewhere, what do they do as time goes forward. The problem with quantum chemistry is that it's very, very, very expensive. So you can predict what happens to two atoms as long as they're not too heavy, as long as they only have a couple of electrons. And you can predict them essentially with arbitrary accuracy. But we are very rarely interested in just a couple of atoms. So what we want to do is to understand things up here about macroscopic objects, about cells, about proteins. So in between, there's a whole bunch of techniques that are systematically approximating the equations of quantum mechanics with, as you go up here, with more and more capability, but less and less fidelity. And typically, when you're a scientist working somewhere along this length scale, you pick the method which is appropriate for your question. If your question is about proteins, you will ask where the atoms are. You need hundreds of thousands of atoms to model your system. You will pick an appropriate method. If your question is about a drug molecule and what happens when it gets metabolized, what happens when a hydrogen atom gets stripped off of it, you will do quantum mechanics to figure out what happens to that particular atom. So when you make these models, normally you work top down. And that's generally how we model things in science. So you have a question at some level, you create a model, maybe for the level underneath, you parameterize it, you test it, you validate it, and you work your way down in understanding. But there's an opposite way of working, which is called first principles modeling. So that works from the bottom up. We know how quantum chemistry works, just we can't execute it for too many atoms and too long a time. So let's find approximations, systematic approximations of quantum chemistry on the higher length scales and see what happens. And we can do the same thing from quantum chemistry to density functional theory to force fields. And this has had phenomenal success over the last few years. I'm going to show you some examples. But what machine learning enables us to do is to do this systematically without essentially loss of accuracy. So that's called free lunch. That shouldn't be allowed. But in some cases, it really does work. So the example, you can do that to quantum chemistry. So you can think about how wave functions behave, and you can coarse grain them into electron densities, and you can gain a factor of 1,000,000 in efficiency. And there are some people who do that. That's very hard. The next level is thinking about how electrons behave with electron densities and distilling that into a force field. How do the atoms move around? And that's another factor of 1,000,000, and that's the business that I'm in. So what is first principles molecular dynamics, and how has it affected us and affected our understanding of the world recently? So recently, I mean the last few decades. So we can compute phase diagrams. So here's a phase diagram of carbon in gigapascal, 500 to 1,500 gigapascals of pressure. So that would be 500 will be the center of the Earth. 4 times that will be the center of some larger planet. temperature, 2000, 4000, 6000 Kelvin. Again, 6000 Kelvin is the surface of the sun, and also the center of the earth. So we can't conduct experiments on that, under those conditions, but we can do computation. And we have models that are good enough, density functional theory is good enough to predict what carbon is going to do under those extreme conditions. We can look at aqueous solutions of polyatomic ions, something that is an important part of the processes that goes on in liquid chemistry and also in our bodies. And we can't probe that experimentally in atomistic detail, but using molecular dynamics, we can understand the structure and dynamics of these systems. And then there is surface science, another example of great successes of quantum simulation. So we can take, this is, I think, a TiO2, titanium dioxide surface. It's a catalyst, and you can take molecules, absorb them on the catalyst, and this is what the experiment looks like. So you see certain molecules under some contrast condition, but you don't actually know what they do there. And you can do molecular simulation to find out. And this is big business in the, not in the commercial sense, but just in the sense of importance. So this is the usage of the UK National Academic HPC facility. And I've colored the codes that execute, that are run on there. This is the percent used for each code. And I've colored all the green ones that are doing quantum simulation, quantum mechanical molecular dynamics. And the red one is doing force field dynamics. And you can see that about 40% of our academic use in the UK goes towards doing quantum mechanical molecular dynamics. And that's it's a bit controversial to say, but it's a little bit of a waste of time if we could do that 1,000,000 times faster. If we could do molecular dynamics without computing, without using the electrons, just move the atoms, then we could do either save all this time or do many, many more things. So what is actually happening in ab initio molecular dynamics? So we have atomic positions, R. We solve the Schrödinger equation in some approximation. At each time step, we get wave function psi and the rho of R, the electron density, and that leads to forces on the nuclei. And then we use Newton's law. So just update the atomic positions with the forces, and those forces are gradients of an energy. And then we throw away the wave functions. We throw away the densities. We don't use it in the molecular simulation. It's only there to move the atoms. So what if we could never compute them? We didn't have to compute them at all, and we just went directly from atomic positions to the forces on the nuclei. That's called a force field, and essentially means taking this potential, the gradient of which are the forces. It's a function from 3 n dimensions, the positions of all the atoms, to a real number called the energy. And if I could model that function in some complicated nonlinear way, if I knew how to do that, then I could save all the quantum simulation and just do molecular dynamics directly. I wonder what we could do to use that. You know, nonlinear functions, high dimensions, complicated behavior. I think a lot of you know where this is going now. The quantum chemists have been actually doing this for decades, since the 1970s, with very, very different techniques that, well, we are all engaged in here now. The problem is that those techniques do not scale. So they've been able to do it for just a few atoms. Those are exponentially scaling methods. And so the question really is how to do this in general, for materials, for large molecules, for molecular assemblies. So I'm going to now summarize 10 years of very exciting and intense research in one slide. It's going to have a couple of equations in it, but I promise that that's the only one. So we want to have a representation of molecular geometry based on which we will then make nonlinear models. And we want to have rotational and permutational symmetry. So if I rotate my set of atoms, the energy doesn't change. If I swap around atoms that are of the same type, I swap hydrogens, I swap carbons, energy doesn't change. So a classical way of doing of starting out is to write the cluster expansion. I have an energy, X is the collection of atomic positions, little x j enumerates the atomic positions for each atom j. And I have some baseline energy, and then this is a sum over all atoms. F1 is a function that I will need to parameterize, but it only depends on a single atom. F2 depends on the coordinates of 2 atoms, and Fn ultimately depends on the coordinates of all the atoms. And I'm looking to this expansion because in principle it's exact, but I want to truncate it. So the idea is that we will not need all n terms. But you see these sums. So if I have a function that depends on 2 atoms and I want permutational invariance, I better sum over every pair of atoms the same function. And when I have 3 atoms, I better sum over every triplet. So that sounds a bit scary and seems expensive. But this is how one would do this. So you take some basis phi, that's a basis for real space, that's basis for a single atom. And then you construct a tensor product basis. So if I want the basis for not r to the 3, but r to the 3n, I can take a basis for r to the 3 and just tensorize it. So take products of that basis function, and these products are a basis for r to the 3n. So I can construct basis functions for my full space. Ck could be expansion coefficients for my function, and I have I have to sum over all the possible ways I could create the basis functions. The big problem is here, that I have to sum over all possible permutations. Sn is the symmetric group of permutations of n particles, and I have to sum over all possible assignments between my particles and my basis functions. And when n goes large, 2, 3, 4, 5, that gets very, very expensive. So we're going to do a trick. So first I write the cluster expansion just as before, but I've used U's instead of F's because I'm going to drop the constraint that I sum over each pair just once or each triplet just once. I'm going to sum over J1, J2 for the pair unconstrained. So I hit each pair twice. And when I do J1, J2, J3, I'm going to hit each triplet 6 times. Sounds like a waste, okay? So I'm symmetrizing this product, but and that of course translates into, instead of summing over the symmetric group, it just means summing over all possible assignments of atoms J and how they are assigned to basis functions. Sounds like a colossal waste, except that now I have a tensor product structure, so I can rewrite this. I can swap the sum and the product. So this sum and this product is now swapped. I can bring the sum inside, and I sum a single sum over J, sum over my basis functions. Then I do the tensor product. And when you product a sum, you get all possible combinations. That's amazing because I've gotten rid of an n factorial cost. Okay, so that's it actually. So to understand it that simply, it's taken us a long time, but it took us many, many small steps to get there. But that is essentially the key idea. So let me give some names to things. So I have a single particle basis phi. When I sum over all particles just once, that we call a one particle basis because each term here just has one particle in it. Then I do the tensor product. So that's now a permutation invariant many particle basis for my functions. And then I want rotational invariance. So let's again do it naively and see where that leads us and if we can do better. So if we want something to be invariant over rotations, let's just average all basis functions over the rotation group. So I take every basis function, G is an element of SO3, and I just integrate all basis functions over the rotations. Sounds bad. But if we can do this, then finally I can make a model for the energy. It's just a linear or non-linear. If you want to we'll plug it into a neural network, but it's just a model based on the, off of these basis. Now, permutationally, rotational, invariant basis functions. So what about this, this integral? Actually, it turns out that the problem has been solved for us already, because if you take a very special basis for phi, the spherical harmonics, and then whatever radial basis function set you want to take, this is the form of spherical harmonics. It's an exponential in the spherical angle, so exponential in phi, and this is an associated Legendre polynomial. You can all look it up in Wikipedia if you want to know the functional form. Then it turns out that this integral is analytically doable. When you do it analytically, it turns out to be just a linear combination. The B's, the rotational invariant basis, is just a linear combination of the A's, the non-rotational invariant basis functions, with coefficients that are in a very thick textbook that is in every university library. They're called the Clebsch-Gordon coefficients. That's it. So these all become truncated expansion coefficients. So typically the number of terms here would be a few hundred for a very good model, maybe 1,000 for a very, very accurate model. And there are other tricks one can do to do with embedding. So one can take linear combinations of these and reduce that further. But even a naive evaluation of what I'm just showing is very, very, very feasible. And I'll show you some examples. So this stuff has really revolutionized how we do force fields. And here are two reviews from a couple of years ago that I was involved in. The first one talks about representations. And this is a family tree of all the different representations that people have come up with for force fields in the last 10 years, and kind of puts them on the same footing using the formalism I've just outlined. So many of them turn out to be special cases. And the second one is more of a modeling paper, taking a particular version of this basis set and showing how you actually model materials and molecules. Both of them are 80 pages, so they're really bedside reading for several months. So here's why this is a revolution. So my background is materials rather than molecules, so I'll start with this. And here's the favorite material of all material modelers, silicon. And I'm showing you percentage errors with respect to a very good quantum mechanical target baseline of all the traditional models. And these are, each bar is a different property. So there are elastic properties, surface properties, defect properties, point defect properties of this material, and interface properties. And you can see that errors are tens of percents with respect to the quantum target, and many of them in this magnitude are kind of useless for predictive modeling. And the ML model is the red one. So you get a uniform drop, simultaneous drop in error to about 5%, and it's controllable. So if I turn up the basis set, I get a better model. And here's what the kind of things people can do with it. So here's a simulation now of 500,000 atoms of germanium antimony telluride. That's a material in phase change memory. And it's arrayed in some sort of grid like this. So you take a grid of electrodes, and in between each pair, you have a bit of this material. And when you pulse it with a current, it amorphizes. And when you pulse it again with a bigger current, it crystallizes. And those are your 0 and 1 bits. And so the resistance is different. Here's the validation. So you can run this pulse in a small set where you can afford the DFT, the quantum mechanical calculation. And this is what it looks like when you do it with the ML model. That's much, much, much faster and scales much better. So you can actually then go and simulate the real device. So this is the first time we are able to do an atomistic simulation of a 20 by 20 by 40 nanometer memory device on the scale in which it exists in the chip. And you can then study the different kinds of heat pulse trains, see if you can store more than 2 bits by amorphizing it halfway, and so on. So this has never been possible before. Here's another example this time on catalysis. So we are trying to build potentials to be able to study the changes of small molecules on active surfaces. The example here is carbon dioxide turning into methanol. You can all understand why that's an important reaction, and it's going to these kinds of reactions are going to be important for surviving the future. So this is indium oxide, and we've created a potential using the ML technology by iterating a few times. You run a little bit of MD, see where it goes wrong, you put it back in the training set, but this is not a long, complicated process. We put in a bare surface, a few fragments, and 2 rounds of iterative training, and that allows us to make a potential that can reliably carry out this reaction from beginning to end. And we chose this particular reaction because it was extensively studied with density functional theory. So we knew what we are supposed to get, and we were able to reproduce the reaction path that the paper that studied this quantum mechanics produced, except that we had a much faster potential. So you're able to conduct extensive searches in path space. And immediately, when we started doing that, you discover here that in the rate limiting step, the step with the highest barrier, the actual barrier is half of what people found with the expensive quantum method, just due to lack of sampling. You cannot enumerate the paths if you have an expensive method. The other thing you can do is ask, do people even know how these fragments adsorb on the surface? So here's the absorption site of carbon dioxide on the indium oxide surface as optimized with the very expensive DFT method. But now we have a fast potential. So actually we can do many such optimizations. In fact, we can do thousands of optimizations and study the whole distribution. And you find that in fact, there are many, many, many more different sites which are quite similar in energy. And in order to study the reaction properly, we need to study all of these adsorption sites and try and make the reaction happen from all of these. So that's obviously ongoing work, but at least now it is possible. So then as we move into molecular systems, it turns out that what I've shown you is good, but we can do a lot better. And that's when we go from the linear modeling, linear many-body basis, we move over to message passing networks, but we keep the good properties. So here's a representation of an atom with its neighbors, and we can create the A spaces as I've shown before. So let's do that. We copy the atoms from the neighborhood and we create the ACE representation, and we do that on every atom. But instead of then fitting the energy just to those basis functions, now we communicate between each pair of atoms within some cutoff distance. We communicate the entire expansion and we re-expand. That's called a message passing neural network. And here's a paper with benchmarks on this scheme that was put online a few days ago. And the only reason I put it up here, deliberately too small, I'm not trying to explain to you the equations, but these 10 equations describe the entire message passing neural network, not with funny boxes and labels and blocks, and you have to dig into the code and what they mean. This is actually what's going on. These equations define you the mathematical form of this network. And it is very similar to what I've shown you. There is one particle basis, there is an atomic basis with permutation invariants, a many particle basis, a symmetrized one with the Clebsch-Gordon coefficients, and then we do pooling and node feature update as is customary in message passing networks. And in fact, the only nonlinear activations are in the definition of the radial basis. So we have a radial basis, that's a one-dimensional function. We want it to be flexible, no other nonlinearities. So what has this done? What does this bring us? So here's an example now closer to medicinal chemistry. Here's a small molecule, a barial with 2 different rings and rotatable bonds. So there are 3 rotatable bonds here, and that's the alpha, beta, gamma angle space. And we've computed the potential energy surface with density functional theory. And what you see, that's one of these surfaces is here. And you see the traditional force fields are kind of qualitatively right, but they're they're not actually. I mean, this potential energy map here looks quite different from the one here. The top left and the bottom right is what we get with the simple ACE-like expansion or its equivalent when you do 3-body. So 2-body, 3-body, F2, F3. And they're actually quantitatively better than the classical force field, but they're really not that great. They're cut fuzzy, they're not very smooth. Once you do the ACE expansion, you get something that's really very, very accurate and visually matches density function theory, but we can do a lot better. So here are cuts of this surface, and the orange line, the black line is DFT, the target. The orange line here is the ACE expansion. Sometimes it's good, sometimes it isn't. And when you do the message passing network, then you really fall on the line. So here's the best one. The purple line is the MACE model, the multi-ACE, and that really falls on the line even when it wasn't trained. So there are some of these cuts are very far away from the training set. This was trained for that molecule directly, but can we do a general organic force field to replace what people are using before? So that's what we've done here. This is MACE trained on the SPICE database, and I'm showing you torsion angles. So these are the similar curves as the ones here. So in a particular molecule like here, you rotate around this single bond, and this is the energy. And here the black is the quantum chemistry target, even better than DFT. This is coupled cluster. And the empirical force field that's in general use is the blue one. The first ML model from a few years ago from other groups is the orange one. Sometimes it's okay, sometimes it isn't. And the red one is essentially indistinguishable by eye from the quantum chemistry target. And you see that in here, this is the mean barrier height on these dihedral rotations, and essentially we recover the DFT error. So I want to close with ideas about generative modeling. A lot of posters and a lot of discussion here is about generation rather than regression. And I'm getting interested in that, and partly I came here to learn about that. So here's a generative problem that's quite different from what people have been talking about. So here's a set of carbon nanotubes. Carbon nanotube is a tube, is a material made of carbon that looks like this, what's on the bottom, and you can make it in various forms. Here's a carbon nanotube forest, and the image of this image that you see here is about the width of a human hair. When you blow up by a factor of 2, you see the individual strands. You blow up by a factor of 50, you see that these tubes are sort of they're not straight. They go around. They're a bit irregular. So how do we model this? How do I create an atomistic model that represents these irregular carbon tubes so that I can study their properties? So we've coded up a diffusion model with MACE as its score function and generate local environments with the construction and healing. And here's what happens. So let's see, I better show it to you here. So we start and we create local environments that look like the training set. It's been trained on a generic set of amorphous carbon models. And what you see is that it generates a periodic tube-like structure. Now, this is just a toy. This is an experiment, the result of a month of graduate students poking around. But I hope that in the future, we can do these kinds of things where we look at experimental images of not quite atomic resolution, and we are able to backfill and see where the atoms are with a combination of quantum mechanical knowledge and ability to do generative modeling. And what I'd really like to do is something like this, which is replace molecular dynamics by generative modeling. So here's the kind of vision. Here's the example. We haven't done this yet, but here's the example. So a couple of years ago, we used one of these fast ML models to simulate amorphous silicon at high pressure. It's 100,000 silicon atoms, 2 million MD steps, altogether 10 to the 11 calls to the atomic forces. It took a month of supercomputer time just to prepare the system. The system, an amorphous silicon looks like a network it's sort of represented here. You can see this big cube, and if I zoom in, you can see each little segment here is a silicon bond, and it's amorphous, so it's not periodic. I'm representing it in this huge box, but the real one isn't periodic at all. And just to generate this structure took us the whole month on the supercomputer. And then the science could start. What the science is actually then compressing it and seeing the amorphous system crystallize. So that's what you see here. But the system is quite homogeneous. Why can't I learn what the local environments look like and generate an arbitrary sized amorphous crystal using which I can then study amorphous science? Here's what the simulation, the expensive simulations look like. What you're seeing here is a molecular dynamics simulation where the color represents speed, essentially, displacement of atom. And what you see is that at the beginning, there's a lot of displacement, and at the end, there's hardly any. The system has frozen from a liquid state into the amorphous state. Let me run it again. So first, everything moves around. It's a liquid, lots of high yellow color, lots of things are moving. But as the system cools, and this cooling is over 10 kelvins, so a very, very narrow range of temperature, you freeze the system. And I've selected a few atoms, and these white lines are trajectories of an individual atom. And you see that they start out moving and then they stick around. So we couldn't have possibly done this quantum mechanically. We've done this with the ML model, and that's fine, but it was still a month of computer time to generate this amorphous structure. I'd like to do that using generative modeling, and I'm here to learn about that. So thanks very much, and I'm happy to answer questions.
Thanks a lot, Gábor, for the great talk. It's really good to see some material science also instead of just drug discovery. And yeah, if you have any question, please go to the mic as usual.
So do you train your diffusion model using just squared error on the scores that you're getting from the energy function?
Yes. So this one this diffusion model was trained in the traditional way diffusion models are trained. So on examples, of small examples of amorphous carbon, and then that's the generation step. And that's so terrible that then we did a healing step in which we locally then relax using the energy model. But that's not really right. I mean, I should be training using the energy function, but we don't know how to do that.
Yeah, I think it shouldn't be too hard.
Yeah.
So you would, is that the main limitation of the current approach with that you've explored for the generative part? So
it's very, very early days. This generative model is not easily controllable. The structures it gives are okay, but they're not yet usable, I would say. So I wouldn't say that they're usable yet for any scientific purpose. They are not random. They kind of look like the thing that if I go back to the nanotube that we generate, I wouldn't know how else to create this defective nanotube. A perfect nanotube is easy to create. It's a mathematical definition, but real nanotubes are not perfect. I don't know any other way of generating it, but this doesn't look that good. It's a bit too disordered. I'd like to control the amount of disorder. I'd like to be able to put in curvature or some persistence length. I don't want to define that it's a circle or how, but it should be straight up for a few tens of nanometers and then bend. I don't know how to put that kind of control into it.
These quantities that you'd like to condition on, can you compute them once you have generated a
for sure. They are very straight, very simple geometry.
So then you could condition, I mean,
so that's,
you basically create that relationship between those variables and the conformations, and then you could train to condition.
Yeah, the big thing that I don't know how to do is how to make the model scale independent. So I don't want this one with this many atoms. I want arbitrary length.
Yeah.
Because it looks the same locally. It should be possible to have a single model which I can just keep running.
I don't think machine learning has the answer to this yet. But one thing I've been like dreaming of for a while now is, think of what deep learning is supposed to be about. It's supposed to be about discovering abstract representations. And that's exactly what we humans do when we make up quantities that don't exist at the low level in nature, but that help to represent the distribution more compactly, or at least some aspect of it. Like we invented pressure and temperature. They don't actually exist as the low level quantities. So I think that it's conceivable that in future years, if we really focus on this ability for discovering latent abstraction, so latent as in it's not something you hard coded, but they are like random variables that when you introduce them in the modeling step, they allow the model to be much more compact in order to express the same distribution.
I think that's right. If I showed you lots of examples of nanotubes like this, the model should discover that they have a persistence length, that they don't bend every nanometer. And in fact, I don't know what the real persistence length is. I don't know it as a number ahead of time. There's no law of physics that tells you that. That has to come from the data. But I also know that if the model doesn't discover it, you'll never be able to generate arbitrary sized models. So that's something that really I want to think about.
Thank you.
So since there's no more question, let me ask a question on my side. So right now you've shown how we can make force field extremely more accurate, but in many applications, speed is more important than accuracy. So how can you, like in future work, what's your perspective on speeding up molecular dynamics so that it's as fast or even faster than traditional force fields?
I think quite properly, this is being solved from both ends. So there are people who say, let's have force fields that are as fast as the empirical ones, but a bit more accurate. Okay, and there are people like me who say, let's make it very, very accurate, and then think about speeding it up. And currently, the difference in speeds is like 100 or 1,000 between those, but it's getting better. And I think for the particular ML models that I'm making, I think software engineers writing better CUDA kernels, custom hardware. There are hardware vendors around here at this workshop who I'm keen to talk to about this kind of thing. So I think we can make these things faster. I'm not sure that they will ever be as fast as a 10-parameter empirical model, which deliberately loses all the accuracy. I don't think you can predict a quantum mechanical force with 3 flops. But I think we can close that gap substantially.
Yeah, that makes sense. So that we can still, like, instead of having to go to 1,000 times slower, maybe go to 5-10 times slower, but recover a big chunk of the accuracy. Okay, thanks a lot.
Thank you.
No more questions. So a big hand of applause for Professor Gábor.